because we need to worry about those 10 to the minus 23rd numbers too. So what are some other properties of floating point math? Well, first, we also do need a rounding rule, right? So the fact of the matter is, when I do arithmetic with floating point numbers, sometimes I'm going to multiply things, and I'm going to get something that I can't represent, usually the lowest order bits, yeah? So we need to specify very carefully how you round numbers up, down, to the nearest, to the highest, to the lowest number representable. And something you have to be careful about if you're an engineer at IEEE and working on these sort of number systems is that you don't want to accidentally introduce bias into somebody's calculations. Right? So for example, what would happen if I took all of my numbers and every time that I did an inexact calculation, I rounded up to the next number that is representable in my number system? Well, slowly, as I'm doing more and more math, right, maybe my system is literally adding together 4 billion numbers, right? Then I have the chance to add together 4 billion least significant digits that are wrong. Now, 1 or 2 of those isn't such a big deal, but eventually these things can start to accumulate, and what you don't want is that you accidentally always get numbers that are larger, right? So usually what we do when we design a rounding rule is you say, okay, in the case of a tie, we're going to round, for example, to the closest even bit, right? Something that's sort of symmetric so that what you don't end up doing is accidentally biasing your calculations toward big or small numbers. Does that make sense? Yeah. So in fact, this little phrase, round to nearest ties to even, is the one that I think is implemented in the IEEE standard, which I had the pleasure of reading on a bus in Europe a couple months ago. Anyway, so the one last thing that we can do, we can say, okay, is there ever a time, so now this is specific to the binary system. Is there ever a time when I would want to have 0.1 times 10 to the, 1? No, I can always make my most significant digit a 1. Yeah? And so in fact, if we're writing a piece of hardware that only has so many slots for storing a number, we don't need to keep storing this leading 1 here. We can just assume that all the numbers in our number system always have a leading 1. There's one exception to this rule, which is obviously the number 0, which has no leading 1. And usually there's a special case for that. So like the number with all bits equal to 0 is just automatically the number 0, and such is life. In fact, in floating point math, sometimes you can end up with really bizarre cases where you have plus or minus 0, and these are 2 different numbers. But this, I think, for the most part, is handled okay. So anyway, now we have sort of 2 approaches to storing numbers on your computer, right? We have fixed point, and we have floating point, right? This corresponds to singles and doubles on your computer, I think. And for the 99% of the applications that we're going to discuss in this course, those are acceptable. But in that last 1%, occasionally you need something a little more exotic and creative to represent a number. So to that end, we can do things like infinite precision arithmetic. I remember when I first saw this in college, I thought this was such a cool phrase, but it's actually really boring. So the idea here is that you're going to define a number system and you're going to force yourself to stay in it. Right? So for example, let's say that we only care about the rational numbers q. Right? Now what are rational numbers? They're just fractions of 2 integers. By the way, does everybody know this notation? Q means rational numbers, z means integer. This is the first page of my little notes. And then you can write down any rational number as the ratio of 2 integers. Is it necessarily unique? No, you could multiply a and b by 2 there, but you can always write it this way. Right? The nice thing is that if I guarantee that I stay in the realm of rational numbers and I just store 2 integers, then I can do arithmetic without any mistake whatsoever. Right? And in fact, I can write down different rules. So if I want to add a over b to c over d, then I think you guys can probably all find a common denominator and write down a set of rules on just integer arithmetic that gives you an infinite precision representation of the sum of these 2 fractions. Right? So what's the exciting aspect here? Well, the exciting aspect here is that we haven't made any mistakes. We haven't rounded. We haven't, truncated. We could even use some bizarre representation of integers to avoid, running out of bits that way. But on the flip side, the math here is a lot slower, and, well, you're stuck to using rational numbers, right? So if I want to take the square root of 2 in this number system, can I do that? No. So where is this type of math used? Well, oftentimes in actually in the sort of early versions of what I do in computational geometry, you want to know whether 3 lines actually intersected a point or whether they intersected something very close to a point. And when you want to answer questions like that and you want certificates that say whether this is accurate completely, then you start to need this annoying infinite precision stuff. Another thing you could do is bracketing, right? You could say, maybe I don't know my number 100%, but I know that it's in this range. And I'm going to do all of my arithmetic in a way that maintains not just a number, but sort of a little block of numbers where I think something might exist. Right? So in this case, what is the sort of arithmetic you might do? For example, let's say that I have one number x plus or minus epsilon 1 and another that's y plus or minus epsilon 2. Then when I add all these together, well, I get x plus y in the first term. And then I have to add together the error of these two guys and have an upper estimate of the error of adding these two things together. Right? Now, this seems like overkill, but every once in a while we want to have a guarantee that our arithmetic has given us the answer that we expect. And we want to be able to tell our clients that with some amount of confidence your number has some property or another. Now, if you're using IEEE floating point stuff, you can't do that because you don't know if there's some rounding happen in the middle of your calculations and like the least significant bit is actually wrong. But here, if you always apply these error estimates conservatively, then you don't have this problem. Yeah? And in fact, by the way, all of this math looks really annoying to implement, but if you use C++, you can just overload all of your operators, write these things in a class, and it just looks just like standard arithmetic. Of course, you got to be careful, because if you do that, your program might run really slowly, and you might not know why. So anyway, there are lots of sources of errors when you do a calculation, right? I've already complained about a few. Sort of the list that I think is more or less in your textbook are things like truncation, right? We talked about that a lot already, right? If you start removing bits at the end of a number, that's truncation. There's also discretization error. Now, what do I mean by that? Well, let's say that I say that the derivative of a function, dy dx, is sort of approximately equal to y of x plus epsilon minus y. X my epsilon for some small number epsilon. Right? Now, usually in calculus, we take a limit as this thing goes to 0, but on computers, we can't take limits. So we take epsilon to be just some small, finite, positive thing. Right? And this is called a discretization error. Right? I discretized continuous calculus, and in doing so, I made a small mistake. Yeah? There's modeling error, right? Maybe I'm writing a weather system and I didn't take into account the flapping of butterfly wings in East Africa when I'm simulating weather over Texas, but that could have some small effect. And we do make some assumptions about our model when we generate one of these things. There's even empirical constant error. We only know pi to so many digits, and we certainly only know the speed of light to so many digits. And finally, there's user input error, which seems like kind of a corny thing to put there. But actually, the error can come from, let's say I'm making a spreadsheet and I'm like testing out different financial models and I want to play with different parameters. Maybe I'm just kind of throwing different numbers in there. Well, if the accuracy of the number that I'm throwing into my parameters of this financial model are like just ballpark things, then there's really no reason for me to do super high accuracy math on the rest of my system because it's already inaccurate just because of the input. Yep. These are all the kinds of considerations that we should take. So one example that I'll let you think about at home, because we're a little low on time, is what the sources of error might be if you were to do a financial simulation. So for example, if you're trying to solve Black-Scholes or simulate the stock market, what sorts of assumptions could you make that would lead to different types of error when you're doing that in your calculations? And I think it's pretty easy to guess any number of them. So we can classify error in a couple different ways. The first one is absolute error, which is the difference between the approximate value that you're trying to compute and the actual value. Right? So this is sort of our intuition for what error is. How easy is it to compute absolute error? Like if I'm running my iterative root solver or whatever the heck, and I come up with some number, can you tell me the absolute error of my value in all likelihood? No, because if you could, then I could just subtract that number from the value I actually got and got the exact solution to my problem, right? So like all of math would be really boring. So the absolute error is going to be something that we'll keep in the back of our head, but it's not a number that we can actually compute. Similarly, another number we might be able to write down is the relative error, where you just divide by the true value. Now what does this look like? Well, an absolute error might be 2 inches plus or minus 0.02, and relative error might be 2 inches plus or minus 1%. These are just equivalent representations of error. Yeah? High school chemistry. So again, there's a problem here, which is that we don't know the true value, right? We can't compute the absolute value error, because if we could, there's probably no reason for us to make an estimation to begin with. But what we can do is be conservative, right? And oftentimes we can write down upper bounds on the amount of error that our code is going to be making, rather than actually writing down the exact error of a calculation. For example, if I'm adding two floating point numbers, right? What is the maximum amount of error that can be there? Well, it's proportional to the sort of the size of the least significant bit in those two numbers that I just added, right? Is that an exact number for error? No, it's an upper bound, but that's okay because it gives me some idea of the amount of certainty I can have in my calculation. So let's kind of go through an example. So one problem we'll consider in 205A in a couple of weeks is the problem of root finding. Everybody know this notation? We have something like a colon and then the arrow here. This says that f is a function that takes a real number and returns a real number. So for example, f of x equals x squared would be one of these, yeah? And my question is, can we find the x star such that f of x star is equal to 0? This is a classic root finding problem. Now, in reality, it might be the case that our code outputs some number x sub est here, which is our estimated place where f of x is pretty close to 0. Right? Maybe we weren't able to find that 0 exactly. For example, maybe I'm using rational numbers and the root of my equation is square root of 2. Right? Then I'm hosed. I can't even write down the actual 0 of my equation. And I'd like to measure my success. Well, one way that I could do that, obviously, would be to take x star and subtract off x sub est here. Right? And that's the absolute error. But as we said, we don't know x star, so we can't really do that. But what could we do in this case? Ideas?
When the error stops changing.
When the error stops changing. What do you mean?
We keep on reducing, it will go closer to 0, but when it stops changing, we say this converges to a solution.
Yeah. In particular, what goes close to 0?
The value of fx.
Yeah, f of x. Exactly. So there's sort of two equivalent definitions of the thing that I'm searching for, right? One is I'm searching for x star, but we don't know x star. The other is that I'm trying to find a place where f of x is equal to 0. Yeah? So if I take f of x, the estimated x, and I get something that's pretty darn close to 0, then I'm pretty confident that my solution is correct. Right? And this is going to be our big trick for evaluating how good our solutions are in a number of numerical things. And that's called the backward error. So the idea here is, it's a little bit of a bizarre definition, and it's one that took me a long time to sort of get internalized into my head. The backward error of a calculation is the amount that the problem statement would have to change to realize a given approximation of the solution. This is really bizarre, but we're going to do a couple examples, and then you're going to see it's actually not so bad. So let's say that I want to write a piece of code to compute the square root of a number. Yeah? Seems like a reasonable task. So again, remember let's say that y star, is the actual square root of x. And in reality, we actually got some number y sub est, seems to be my notation today. Yeah? So what would be the absolute error here? It's really easy. The absolute error is just the absolute value of y star minus y est. Yeah? We can't compute this number, but that's what it is. Such is life, right? And what is the relative error? Wow, I'm tall. This is great. Well, remember that we take the absolute error, y star minus y est, and I divide by the actual value, right? Yeah, still can't compute it. Such is life. But what can I compute? Well, I can compute the backward error here. And what is that number? Well, the backward error, well, it's the amount that my problem statement would have to change in order to realize the answer that I got. What is the statement? The statement is that I wanted to find the square root of this number x. Right? In reality, I got the square root of some other number. Right? I got the square root of y est squared. Yeah? So the amount that my problem statement would have to change is that minus x. Is this number computable? Yes, we have x and we have y est. And that's the exciting thing here, for me. Similarly, an example that we all know and love is, let's say that we're trying to solve the linear system ax equals b. Yeah? What is the forward error here? Well, let's say that we output x and the actual solution is x star. Yeah? Then what is the absolute error here? I'm not going to bother writing it down. Somebody? Yeah, just the difference between these guys. What is the backward error? Well, one way to parameterize this would be to say you could change b slightly and get a different x. Yeah? This is sort of like changing your problem statement to get the value you wanted. Right? So the actual b, obviously, is b. But the b that you got by solving your linear system equations was a times x. Right? What is this difference, by the way? Well, usually we take the norm of that. And what is this difference? This is called the residual of your linear system. Right? Probably something you've seen before. Right? And it's a measure of how good x is at solving ax equals b. Right? If this number is small but non-zero, it means you have a near solution. Okay. So when we talk about the conditioning of a problem, what we mean is that when you have small backward error, that implies small forward error. That's when a problem is well conditioned. What do I mean by that? Well, remember that backward error is the thing that we can compute, but forward error is the thing that we care about, right? Because that's the actual amount that we got wrong in our calculation. And what we hope is that these things are more or less related. Is that always the case? No. So for example, let's return to that root finding problem and consider two different functions. So here's x and here's f of x, right? And our first function looks like this. And our second function looks like that, right? We're trying to find this root here. Now, which one of these is a well-conditioned problem for finding the root? I got time. The one on the right. Unfortunately, that's not the case. Yeah, sorry. It's it is. So in reality, it turns out the case is this guy. Why is that? Well, what is a small amount of backward error? Well, that's a small amount of space in this direction, right? Because this is the difference in the f of x values. These are the things that we can compute. We don't know how to find roots of f. Of f. Well, what happens here? If I take some bracket in the sort of the y values, right? So here's one intersection and here's another intersection. I get a really wide amount of space for my confidence in x, right? But here, right, I get a very small bracket, right? So in fact, when you're solving the root finding problem, you really want the slope of your root, the slope of your equation to kind of bang right into your root and keep going past. And that's going to be the easiest way to find your root, right? Because if you perturb this function a little bit, you're still going to get more or less the same root. Does that example make sense? Are there any questions there? I see some puzzled faces. No, I'm going to keep moving. All right. Cool. So we can usually write down a number called the condition number, which is just the ratio between the forward and backward error, right? And you hope that this number is, what, large or small? Small, right? So in particular, right, you can kind of guess from this root finding example that you want 1 over the slope to be small, right? Because you want the slope to be, oh wait, did I do this wrong? The forward to backward error. No, I'm sorry, you want this number to be close to 1, I guess. Is that right? Oh gosh, I'm going to get myself confused. You want the forward error to be very small. Yeah, you want this number to be close to 0. Sorry. And in particular, when does that happen? Yes, when f prime of x goes to infinity. And let's do that calculation really fast. Sorry, old man. So what is the forward error of root finding? Well, you can think of this as x minus x star, right? And what is the backward error? Well, it's f of x minus f of x star, right? So in fact, let's write this slightly differently. We'll say that x is equal to x star plus delta x, right? So in the top you're going to get delta, in the bottom you'll get f of x star plus delta divided by f of x star, or minus f of x star. Yeah, hopefully I've done this right. And this number is more or less equal to delta divided by what? F prime of x star times delta. Yeah? This is if you use the Taylor expansion. And these two numbers just go away. You get 1. Right? So this calculation shows you that what you really want when you're finding a root is a nice big vertical function that crashes right into 0 with lots of momentum. Yeah? And that's called the condition number of your problem. When you find that the condition number of your problem is very bad, is very high, now I'm confident. What does that mean? That means that you're unlikely to have a lot of confidence in the output of your code. Right? So the condition number of your system has a lot of bearing on how successful you think that your system is going to be, A, and B, how complicated a piece of code you need to write. Right? If you have a very well-conditioned problem, you can probably get away with a really bad solver. But if you have a really poorly conditioned problem, then maybe you need to start using some of the more sophisticated stuff we'll talk about. So anyway, I would say the big theme in CS205A is going to be that extremely careful implementation is going to be necessary, right? You're going to have to deal with rounding, you're going to have to deal with all of these different approximations and so on, and any number of things can go wrong. For example, this will be sort of our last example for the day, I think. Let's say that I want to compute the norm of a vector, right? Now everybody knows normal vector is the square root of the sum of the squares, yeah? So probably a piece of code that if you've ever done some geometry that you've written, I probably wrote it the other day, is you take a number that's 0 and you just start adding up things squared and then take the square root. Yeah? Gives you the norm of x. Everybody agree? Good. What's the problem here? So let's say the values in x are on the order of like 4 billion, right? Then what's going to be the order of x squared? It's going to be like on the order of billion squared, which is some number I can't even count, right? So very likely, I could accidentally cause overflow in my x's by squaring them, even though the norm of x, right, I take that square root again, so I'll go back from the squared system of numbers down to the square root, right, just the absolute values again, right? So I might accidentally introduce really big numbers in my calculations that I get rid of later. Do you see why this can cause overflow problems? In particular, I might move into another order of magnitude, lose accuracy, and then never be able to recover it. That's not so great. So if I'm really worried about numerical precision, maybe I run my code and I get bad vector norms because I just have big numbers and such is life. What could I do? Well, I could do something that looks way more annoying. I could compute the maximum absolute value of any element in my list. I could divide everything by that number, take the norm, right? And then we know that everything is going to be on the same sort of order of magnitude, right? Namely, 1 is going to be the biggest thing. Sum those, square them up. And then maybe you'll screw up your low precision digits, but you won't overflow. And then you just multiply back when you're done, right? Now this sort of trick, if you're a mathematician, looks totally pedantic and stupid, right? Like this is mathematically equivalent to the thing I wrote down before, but numerically it is not, and you will get different numbers that come out of your code, right? And so maybe we'll do a couple examples. Your textbook has a really surprising example actually, where you solve the quadratic equation, right? ax squared plus bx plus c. Right, and there's that little formula that we all learn in like rhyme in middle school at some point, and it turns out that number is, that formula can be very poorly numerically, behave because you're dividing by something, and they show that like if you do different types of arithmetic on this fraction, you get very different outputs for certain quadratic equations, which is scary. You should all be afraid. Right? Your code could be inaccurate and you don't even know it because mathematically it looks right. Your proof checker is happy with this, but that's not enough. Right, so another example, which I don't think we have time for today, actually looks even simpler, which says maybe I want to take an array of values x and just add them all up. Right? Now what happens every time I add? Well, that lowest order bit that in these IEEE floating point numbers, right, that one all the way on the right-hand side, every single time I add might get rounded up or down, right? So every time I add, I'm multiplying my inaccuracy by a bigger and bigger number, right? It's summing up all the inaccuracies. So you're challenged to think about for the next class, actually, it might be just for reading because it's not the world's most important algorithm, is to think about, can you do this calculation where you sum up all the numbers in a list without inducing an error proportional to n here? That is, can you sum up all these numbers and get an error that's proportional to the lowest order bit? That's what you'd like, and somehow it seems reasonable to ask that. But this algorithm doesn't do that. And to that end, there's sort of a nice little observation that this man Kahan, I believe, made, which is that if you take A and you add it to B, and then you subtract A, and then you subtract B, you don't get 0. Right? That's sort of the point of today's lecture. But what do you get? Well, you get some estimate of the amount of error you induce by adding A and B, right? Somehow the subtraction is safer than the addition here, right? And so what this algorithm is going to do is store a compensation value, which has to do with this difference here, and then try and add it back at every iteration of your summation so that you always keep your error in the lowest order bit. So anyway, I think we'll stop there for the day. My office hours are on Wednesday morning, and then our next class is Wednesday afternoon. Please come chat, start your homework, go on Piazza if you have any questions, let me know if you find typos, all that. And hopefully I'll see you all on Wednesday. It's very exciting for me to have you all here. Cool. Can we turn off the camera there?
Justin, I have a question. Why is there error when you add A and B?
Sorry.